Let's conclude the derivation of the MCMC algorithm by finding the full posterior distribution for the mu sub k's. And the calculation is going to be the same for mu1 and mu2, so I'm just going to do it for a generic value of k. As I said before, it's going to be useful to define n sub k as just the number of observations in the k's component, so the sum from y is equal to 1 to n of the indicators that c sub I is equal to k. And the other quantity that is going to be helpful to define, as we did before, is x bar sub k, that is just the average of the observations in that case component. So this is the sum over the i's such that c sub I is equal to k of x sub I. So the number of observations in the case component and the average of the observations in the case component. Okay, so if I'm trying to derive the full posterior for mu sub k, given the rest of the parameters, what I'm going to need from here is just the terms that correspond to the observations in the case component out of here, and of course the prior that is associated with the case component coming from the prior. I can ignore all the other terms in the posterior. So this is going to be proportional to, first of all, this product over the i's such that c sub I is equal to k of 1 over square root 2 pi sigma exp minus 1 over 2 sigma square xi minus mu sub k square. And then I'm going to have x, if I want, minus 1 over 2 tau square mu sub k minus eta square. Remember that this is proportional to, so I can ignore the 1 over square root 2 pi tau, just as I, by the way, could have dropped this already if I want. So further simplifying this, this quantity is going to be proportional to exp. And now the product goes inside the sum. So I have minus 1 over 2 sigma square sum over the i's such that c sub I is equal to k of xi minus mu k squared multiplied by exp of minus 1 over 2 tau square mu sub k minus eta squared. And if you look at these quantities carefully, you will see that this is just the product of a normal kernel. So inside of here, if I expand the squares, I'm going to get a quadratic form on mu sub k. And then I have another normal kernel. Again, if I expand the square, I'm going to get a quadratic form. So if we're careful doing the completion of the squares, what we're going to get is a normal kernel as our posterior distributions. So I'm going to proceed to do that calculation carefully now. We just derived a form for our full posterior for mu sub k. And it's still proportional to the exponent of minus 1 over 2 sigma square sum over the i's such that c sub I is equal to k of x sub I minus mu sub k square multiplied by the term that comes from the prior exp of minus 1 over 2 tau square mu sub k minus eta square. So to really show that this is going to take the form of a normal distribution, we need to do the expansion of the squares. So I'm going to work with what's inside the exponential. So I can rewrite this as exp of minus 1/2, 1 over sigma square sum of xi minus mu sub k square. The square is outside, plus 1 over tau square mu sub k minus eta square. So I'm going to work with this expression, with these two terms aside, and then I'm going to just plug it back. So as aside, I'm going to have 1 over sigma square sum of xi minus mu sub k square, and the sum i's such that ci is equal to k, plus 1 over tau square mu sub k minus eta square. It's going to be equal to, so expanding the squares, I'm going to have 1 over sigma square sum over the i's such that c sub I is equal to k of xi square minus 2 times mu sub k times the sum over the i's such that ci is equal to k of xi plus mu sub k square, again summed over the indicators, but I have n terms in this sum, and they all correspond to mu k square, so I can just substitute the quantity n sub k that I had defined before in there. And I have the terms that come from this expansion, so I'm going to have a 1 over tau square mu sub k square minus 2 mu sub k eta plus eta square. So now, trying to pull similar terms together, we're going to have n sub k over sigma square times mu sub k square. That's this term right here. Plus, the next term is going to be the one that comes from here. That is 1 over tau square multiplied by mu k square. Minus 2 times. I'm going to go now with the terms that are linear in mu sub k. So I'm going to have 2 times mu sub k. Now, if you look carefully at what this is the sum of the observations that are in the case component. The sum of the observations in the case component can be represented as n sub k multiplied by x bar k. Remember, this is the average of the observations. When you multiply by the number of observations, just gives you the sum that we started with. So that's this term here. The next term is going to be this one. So minus 2 times mu sub k times eta. And then finally, we have the two additional terms. And excuse me, we're missing, of course, a sigma squaring here from this product and a tau squaring here from this product. Very important to remember. And finally, we have a term that is 1 over sigma square sum i's c sub I equals to k of xi square plus eta square over tau square. And just compiling terms together, we are going to look at this as n sub k divided by sigma square plus 1 over tau square that multiplies mu sub k square minus 2 times mu sub k that multiplies n sub k x bar sub k divided by sigma square plus eta divided by tau square plus the leftover terms, 1 over sigma square sum over the i's such that c sub I is equal to k of xi square plus eta square over tau square. So now that we have written the expression in this form, it's clear that the term inside the exponential here just corresponds to a quadratic form on mu, and we can do a completion of squares to find the expression for the full conditional of mu sub k. Using the side derivation that we just did, we can rewrite now this expression as being equal to the exponential of minus 1/2, and then all the terms into which we simplify this expression. So we're going to have n sub k divided by sigma square plus 1 over tau square multiplied by mu sub k square. We're going to have minus 2 times mu sub k that multiplies n sub k x bar sub k divided by sigma square plus eta divided by tau square. And then we're going to have the extra terms, the 1 over sigma square sum over the i's, such that c sub I is equal to k of xi square plus eta square divided by tau square. Now, as you can see, this expression here doesn't really depend on mu sub k in any way, so I could break this into two terms, two exponential terms that multiply each other, and because the one that involves these terms doesn't have mu sub k, it can be dropped out of the proportionality. So I can just write this in turn as being proportional to the exponential of minus 1/2 n sub k divided by sigma square plus 1 over tau square mu sub k square minus 2 times mu sub k n sub k x bar sub k over sigma square plus eta over tau square. So I just discard these additional terms. And finally, to get the structure of the kernel to look like that of a normal distribution, I just need to carry out completion of squares, which is one that you should already be familiar with. And again, there is going to be an extra term that doesn't depend on mu coming out of the completion of squares. And that extra term can be dropped out just in the same way that we dropped these two terms out there. If you do that calculation carefully on your own, you will find that what you get is that this is in turn proportional to minus 1/2 n sub k over sigma square plus 1 over tau square that multiplies mu sub k minus two terms in the numerator n sub k x bar sub k divided by sigma square plus eta divided by tau square, and in the denominator n sub k over sigma square plus 1 over tau square. And if you look at this carefully, you will see that this looks like the kernel of a normal distribution, where this term here is, you can call it eta star if you will, that it's the updated mean. And you can see this term as being the precision of the updated precision. So this term is essentially 1 over tau square star, if you wish. So in other words, my posterior distribution for mu sub k, given all the parameters, it's going to be a normal with updated parameters eta star and variance tau star square. And this is your traditional normal calculation that you have probably done many times in the past, where you can see that the variance of the posterior is just the harmonic mean of the variance in the prior and in some sense the variance in the likelihood. And where the posterior mean, it's going to be a weighted average of the mean in the prior, that is eta, and the mean in the data that you can think of as being x bar sub k.